In this talk, I now want to make some observations about the examples that I constructed in the previous talk with respect to the moduli space of deformed G2 instantons and the Chern-Simons type functional. So to begin with, when one talks about deformation theory and moduli spaces, one of the key questions that you want to ask is the deformation theory unobstructed or obstructed? So in this setting, what unobstructed means is that the moduli space of deformed G2 instantons is a locally smooth manifold of the dimension you expect, which is 0. And what that means is that if you look at the linearized DG2 instanton operator, which I'll call curly L, then it has to be surjective. And this comes from the implicit function theorem. So if you know that L is surjective, then you can solve for any infinitesimal deformation uniquely, and so you get that the moduli space is a smooth manifold of the expected dimension. And what is this linearized operator? It can be written as follows. You take a half the curvature of the connection squared plus star phi, and then you wedge that with D. That is a map from the 1 forms on your 7 manifold to the exact 6 forms. And the reason why it's a map to the exact 6 forms is because both star phi and fa squared are closed forms. So D will commute with these with the wedge operation. So this just arises from linearizing the DG2 instanton equation. And as I said, that means, by the implicit function theorem, whenever you have an infinitesimal deformation, you can extend it to a genuine deformation. So what does obstructed mean? It means that this linearized operator is not surjective. And so that means your moduli space may not be a smooth manifold, or if it is smooth, it's not of the dimension that you expect, i.e. it's not 0. And from these observations, it's then very clear that if you have the non-trivial DG2 instantons that Gonzalo and I constructed for the nearly parallel G2 structures phi ts and phi np, then they have to be obstructed because the moduli space is not 0-dimensional in those cases. So for the trivial DG2 instanton, you'd expect that to be unobstructed because that thing is isolated. It's just a point in the moduli space. And indeed it is for the nearly parallel G2 structures phi ts and phi np. But it turns out that it is obstructed if you choose that special value t is 1 over root 2 for either the plus or the minus family. Remember, that's exactly the point where these non-trivial families of DG2 instantons died as I moved from t is 0 to t is 1 over root 2. So, how do we prove these results? Well, what we do is we use the deformation theory developed by Kawai and Yamamoto. And what they show is that being unobstructed for this moduli space problem is the same as being rigid and isolated. So when we look at our pictures which describe our families of DG2 instantons, we see that if we take a nearly parallel G2 structure, either phi np or phi ts, we see that for the non-trivial connections, then we either have an S2 family or an S1 family. Those are continuous families, and so the connections are not rigid and isolated, and so they must be obstructed. But we see at t is 1 over root 2, then something interesting is happening. You see, away from there, then the trivial G2 instanton, that's just a point, the moduli space in that case, in both cases. And so it is indeed rigid and isolated. But here, there's the possibility that it could be deforming in the direction of the blue curve. And indeed, one finds that there is an infinitesimal deformation of the trivial dg2 instanton at this point. But even though it's isolated, it's not rigid, and so it must be obstructed. And to see that there must be an infinitesimal deformation, we actually use the Chern-Simons type functional that I'm going to mention a little bit later in this talk. And that's one reason why I like this proof, is that we get to use the variational perspective on dg2 instantons. Now, I should also say that one can see that the moduli space of dg2 instantons on the trivial line bundle for each of the nearly parallel G2 structures, it has different dimensions. We see it contains at least two components of different dimensions, because we have here the point in S2, and those two things are not connected, and we have a point in S1, and those can't be connected because of the moduli space theory tells us this is an unobstructed, rigid, and isolated dg2 instanton in each case. And so what that's saying is that it's going to be a challenge to study the possibility of enumerative invariance with dg2 instantons, because one wants to build invariance by looking at the moduli space. And here we have components of different dimensions to deal with. That said, one should expect to throw away all of the components that have dimension bigger than 0. And so indeed, one might throw away these points. Okay, so that's enough for the moduli space theory. I now want to go on to the Chern-Simons type functional. So the Chern-Simons type functional can be defined in the following way. So we start off with a reference connection A0 on some line bundle L, or U1 bundle if you prefer, on the 7 manifold with the given G2 structure phi. We then take our connection A on L that we want to compute the functional at. And so we can define a path between our reference connection A0 and our actual connection A that we want to look at as follows. We take A0 plus A minus A0, so just the straight line path from A0 to A. And of course, that's not a connection on X, but on X times 0, 1, where S lives between 0 and 1. So that's now an 8-dimensional manifold. And of course, it's a connection because it's an imaginary valued 1 form on that 8 manifold. And so it defines naturally a curvature 2 form, which we'll call bold F, just because we called this one bold A. And so the functional, which was defined by Karagiannis and Lung, is defined as follows. It's defined as is exactly defined so that if you have a dg2 instanton A, then they exactly correspond to the critical points of this functional. That says that curly f of A is the integral over this 8-manifold x times 0, 1 of this form, e to the f plus star phi. And what this means is that you take each of the components of this expansion which are of degree 8. So you throw away anything that isn't degree 8 when you do this expansion, then you integrate it over here. And you can write that down explicitly as a polynomial. But I prefer it this way because it looks much more natural. In any event, this gives a completely variational characterization of dg2 instantons as critical points of a functional. However, it says nothing about what type of critical point a dg2 instanton is. You may see in some of the other talks that G2 instantons, at least in the case of G2 manifolds, turn out to be minimizers of the Yang-Mills functional. So we can ask, are these going to be minimizers or some other type of critical point? Well, let's recall that in our examples, we wrote them in the following ansatz. So they were defined by 3 numbers, A1, A2, and A3. Here, eta1, eta2, and eta3 are the left invariant coframe on some finite quotient of SU2. And so what we discover is that the restriction of this functional f to this ansatz turns out to only depend on two variables, x and y. And what those variables can be described as is just the third component, a3, and y is up to a sign, the square root of a1 squared plus a2 squared. So this is very neat because it means that we can actually start to draw some pictures of what this functional f looks like. And we can analyze its critical points. So let's do just that. So let's consider the case of phi1 plus and phi1 minus. So remember that these two G2 structures are isometric and that phi1 minus is the standard 3-Sasakian G2 structure. So this is the one on the 7th sphere that you would build just out of the round metric in the kind of standard way. And I'm going to sketch the function itself and also give a plot of the level sets. It's a kind of contour diagram. So this is what the diagram looks like for phi1 plus. So it looks kind of uninteresting, that there's a single critical point and nothing else, which is a maximum. And here we have a more interesting situation for the 3-Sasakian one, where we seem to have two critical points up here. So what is happening? Let's have a look. Well, when the trivial connection is the only critical point, which is in the case of phi1 plus, then we have a local maximum. But in the case of phi1 minus, we know that the trivial connection is not the only critical point. And so instead, it's here, and it's a saddle point, as we can see. But our non-trivial G2 instantons, they've now become maxima. So that's our S1 family of DG2 instantons, that these 2 points here correspond to that family, and those things are local maxima for the functional. So we see that things are quite different as we move from the plus family to the minus family, but the interesting GT2 instantons, when they exist, are always local maxima. So let's see what happens when we change the parameter t and we look at the other special case, which is 1 over root 5. So in the case of 1 over root 5, we see the following pictures. So let's remember now that when we take the plus branch of the family, we see the nearly parallel G2 structure phi and p, which defines the squashed Einstein metric, and the other one is phi minus, which defines the same metric, but now is not nearly parallel. So for the plus branch, so for the phi nearly parallel, then what we see is that there's a little dip. You may just be able to see it there where the hand is pointing. There's a little dip there in the middle. And then it goes up to maxima and then drops back down again. Whereas for the minus branch, we have a much more complicated looking situation where we have some maxima, some saddle points. It's all more complicated. So what's happening is that in both cases, the trivial connection is a local minimum. So here it's just a little dip, and here it's again a little dip there, as we can see from this contour plot. But whenever we look at the continuous families of DG2 instantons, so that corresponds to a 2-sphere here. This circle of critical points is a 2-sphere really of DG2 instantons, whereas here these 2 points correspond to a circle of DG2 instantons. Those are local maxima, just as we had in the previous slide. But now we have this extra 2 isolated examples for phi minus of 1 over root 5. They're here, and they are saddle points. So we see that we can get a very unusual mixed behavior of different types of critical points as we vary this parameter t and as we look at the plus and minus family. And what we can see is that if you think about this plus family, this trivial connection must vary from being a local minimum to become a local maximum as I change from t is 1 over root 5 to 1. And exactly when it becomes degenerate is at 1 over root 2. That's that special value we know where the S2 family of DG2 instantons dies. And that explains why you get this non-trivial deformation for the trivial connection that corresponds to the fact it becomes a degenerate critical point. Similarly, as you vary here, those two isolated examples, they get pulled in. So they're here initially, they get pulled in towards the trivial connection and they disappear. So those two saddle points disappear into the middle and you just get a single saddle point. And again, that happens exactly at t is 1 over root 5. Again, it becomes at t is 1 over root 2. And so again, it becomes a degenerate critical point. And so you can prove there is an infinitesimal deformation of the trivial DG2 instanton in that case. So that concludes this talk. And next time, I just want to finish off with a few open problems in the field that I think are worthy of study.